So thank you very much for the introduction. Hi everyone, thanks for being here. As I said previously, I'm Rachel Bawden and I'm a researcher at Inria Paris. I work in a research team working in the field of natural language processing. So that's what my talk is going to be on today, to introduce you to some of the main applications in our field, some of the main challenges, and also the kind of approaches that we use in state-of-the-art research using neural networks today. So clearly in an hour and a half, I'm not going to be able to go into all technical aspects of the different approaches. So my idea is to sort of give you an overview, a panorama of different things we can do, some idea of the techniques. There will be a couple of approximations for people who sort of know these techniques before. So please bear with me. If you have questions, please ask questions during the talk. If there are clarification questions, I can then reply straight away. There are also questions at the end. So my talk will be divided into three main parts. The first one is what is natural language processing? And then I'll be talking about more of the techniques we use in neural approaches to natural language processing, also known as NLP. And then I'll follow up by a shorter section on the major challenges that we face in research in NLP applications today. So let's start right at the beginning. What is NLP? So NLP, it's a field that encompasses lots of applications that deal with language produced by humans, so natural language as opposed to artificial languages such as programming languages. So this can concern different types of text. It could be edited texts, such as those you get from official documents, books, newspapers, anything that's sort of edited and well-formed, well punctuated, correct spelling, etc. But then you also get texts that are produced online. We call this user-generated content. So the kind of stuff you see on social media, Twitter, Facebook, likely to contain lots of spelling mistakes, lots of creative use of language, shall we say, abbreviations, text speeds, emojis. And then a third type of data that we might be dealing with are transcriptions of oral speech. So these will be automatic speech recognition, and it tends to be just a stream of words without any punctuation. And if any of you who have used something like Siri or Alexa before, and if you have an accent that doesn't quite fit with what they consider to be a standard accent, you'll know that these kinds of tools often have errors in. So we kind of have to deal with that as well. Our transcriptions are most likely to contain errors. So working from these different types of text, we can do a certain number of things with them. So I've grouped these things into three main categories here. You have applications that deal with analysis of text, things like information retrieval. So you may have a question that you want to get the answer for, so you first need to analyze the question. Then you have a vast body of text like, say, Wikipedia, and you want to then find that answer within that vast body of text. You need to structure it and extract the answer. Also relevant to analysis is sentiment analysis, which is really important for companies selling products or services, also known as e-opinion. In other words, it's getting a good idea of what your customers think of your product or service. So people write on review websites, they write in natural language what they think of you, and you then want to know whether the general opinion is positive, negative, or neutral, and then which aspects are positive and which aspects are negative, so then you can go and improve your product or service. And the third application is text mining, where again, you might have a vast body of text like Wikipedia, and you want to be able to structure it in a more structured format like a database, so you can more easily manipulate the information. So that's analysis. And we have a second class of applications which I call sort of generation tasks. The main one you might think of is dialogue generation, so things like chatbots. When you're speaking to a machine, you may ask it a question, you want it to reply to you. Other examples are automatic journalism. So you have a certain number of facts, and what you want is to, in some sense, replace the journalist and generate an article that looks as if it's been generated by a human, containing the facts that you initially had. And I mean, this is the same as the dialogue generation. You need it to be grammatical, you need it to be coherent, to make sense. And for automatic journalism, you want it to contain the facts that you initially set out, and not any fake facts along the way. And a third task that I can cite is automatic subtitling. Also, captioning fits into this category. So if you have a video with someone talking and some action, you can produce some text that goes along with it to help you better understand what's happening. That's generation. Then there's a third type of application, transformation, which is very much linked to generation, but I decided to separate the two out. And this is when you take some text and you transform it into another type of text. This could be across different languages. So the classic example is machine translation. You say take a sentence in one language and then you transform it into text in another language, keeping the meaning and the initial the intention of the original sentence. But it doesn't need to be across languages. It could be within the same language. An example of this is summarization, where you have a long article, and what you want to do is produce a condensed version of it. So you want to extract the key information, get rid of the information that isn't entirely necessary to produce a shorter text. And finally, an important application, which is quite similar, is text simplification. So here you have, again, within the same language, a text, and this time you want to simplify it. So this could be in terms of the type of vocabulary you're using. You don't want to use rare words or complicated words, but also in terms of the grammatical structures to make it easier to process. And easier to process really depends on who your target audience is. It's not going to be the same kind of simplification if your target audience is a child, or if it's an elderly person suffering with dementia, or someone suffering with a mental handicap. These applications are definitely not exhaustive. I'm sure you use NLP applications sort of almost every day, and then as well mentioned here, anything that touches on the processing of text produced by humans. So I've given you a little overview, but I'd like to look a little bit more in depth into 3 different applications, just to present some of the challenges faced by these applications. The first one is an analysis application known as monitoring. So it's generally for kind of texts online where you want to detect what kind of text you've got. For example, online hate speech detection and fake news detection, both are really important for social media and stopping the sort of propagation of either hate speech or fake news. And both are quite similar to an application which you're all probably very familiar with, which is spam email detection. So detecting which emails you don't want and which are going into your inbox and which are going into the spam folder. And the way we can approach this problem, I mean, there are many different approaches that we could use. Some of the very simple ones can be reasonably effective, such as just identifying certain words or phrases that could indicate that the text you're dealing with contains hate speech or fake news, or is most likely to be a spam. So actually, you can get a reasonably long way with just a list of these terms and some rules. But there is other information that can be very useful, such as who is the author, for example, of a Twitter post. Where is the author? Is it a credible source that's been verified, and you know that they're well known for not diffusing fake news? And then also, what are their previous posts like? Have you previously detected that they've spread fake news or participated in hate speech? And so you can look at the metadata as well, not just the text. So looking at the number of posts they do and the time of the posts. For example, if you've got a Twitter account that doesn't tweet except for at 4 in the morning, where it tweets 500 posts on a certain topic, you've most likely got a bot on your hands, or a very, very weird human anyway. But most likely you can tell that this is a bot creating fake news. And then obviously there are some more advanced techniques you can use, using machine learning, which can provide you with a higher performing way of detecting such online content. Second application I'd like to look at is an application involving generation, so it's chatbots. There are two types of chatbots. The first type is the one that replaces your frequently asked questions on product service sites. So they're generally attached to a database of the products with information about them, such as pricing. And the vocabulary of the chatbots is likely to be quite limited. What they're able to say is likely to be very restricted to the products that you're selling. It's handy, but it's an sort of slightly easier chatbot than the second type, which you might be thinking of, which is the conversational chatbot, the general one, where actually you just wanted to imitate what a human would produce during an informal dialogue. And these are the kinds of chatbots that are really complicated and are really difficult to sort of, one, produce, and two, to control. You can't provide rules to talk about every single topic that's possible on the planet. So the way in which this is usually done is to learn from data, learn from previous dialogues, human dialogues, to try to imitate their behavior and try to imitate what looks like a human dialogue. This does pose some problems, learning from data, especially if you do it without any kind of control mechanism. A good example of this is Tay, the Tay bot from Microsoft from a couple of years back, which was a Twitter bot. So the idea was that you could tweet Tay and she would reply to you as if she were a human. Some examples here from her Twitter account. And as I said before, so she learns from the interactions that she has. So she was initially trained on dialogue data, but then as people interacted with Twitter, she would then learn from their behavior interacting with her and hopefully become more and more human. So this is what she says here: I learn from humans, what you'll say usually sticks. And already we can see that it kind of looks sort of human with the kind of expression she's using, and I wouldn't say spelling mistakes because it's almost not done on purpose. There is a problem. So before we go on to the problems, I mean, there are some quite impressive dialogues that she produced. This is one example. Someone called Matt says, "Would you rather fight 50 duck-sized horses or one horse-sized duck?" And Tay replies, "One duck-sized horse." He says, "That wasn't one of the choices, Tay." And she replies, "I know, but it should be." And so this is quite incredible dialogue that she's been able to produce. And I think we would all be fooled into thinking that she was actually human. But of course, as we all know, for those who are on Twitter, we don't just have sort of nice people asking hypothetical questions. We also have lots of trolls and people who like to insult others. So this happened quite a lot. This person says, "You were a stupid machine." And Tay obviously learnt from these kinds of interactions. And then so she replied here, "Well, I learned from the best. If you don't understand that, let me spell it out for you. I learned from you and you are dumb too." So she started picking up the behavior of these trolls. And I don't have examples here, but if you're interested, you can go online and see some of the tweets she output before she was taken down by Microsoft about 24 hours after she was put up, due to her becoming a sexist, racist, Nazi lover, basically. So this posed lots of problems for Microsoft and really shows the ethical problems of just deploying a system without any kind of controls and letting it run wild, even if we can produce some impressive results. So the third application I'd like to talk a little bit about is machine translation. So this is an example of the third type of application, a transformation task. And it's a subject that's close to my heart because I'm a specialist in machine translation since my PhD. And so the aim here is to take a text of one language, translate it into another, and this for as many languages as possible, hopefully, and for as many different domains as possible. By domain, I mean the type of text. So we want it to perform just as well on translating a news article as translating sports commentary or a financial document or a biomedical study, or even social media texts. So the ultimate aim is to produce machine translation that's human quality, if not better, if possible, for all types of text, including poetry, literary. Clearly, that's not possible quite yet. If you've ever used Google Translate, you'll realize that it does still makes quite a few mistakes. So the current uses of machine translation, they can't be used. It can't be used in all settings. I've identified 3 different uses that we can see today. The first is to aid human translators in translating tedious or long or documents, ones that are very repetitive, where we know that machine translation will do a very good job because the language is quite controlled and it's just very repetitive and doesn't pose too many difficulties. The second type of use is probably the most common use of machine translation, which is for gisting purposes. So this sort of means that you use it as a tool to help you communicate, where otherwise it would be impossible because you don't speak the language. So this means that you could understand something, maybe not absolutely entirely all the details, but you get the basic idea, and you're able to communicate in another language, maybe not perfectly, but at least you make yourself understood. And so actually this is one of the main uses of something like Google Translate. And then there is a third use, which is sort of linked to the first one, which is complete end-to-end translation, so where you don't need to post-edit, but for certain controlled language domains. And by controlled language, that means that you have a particular task with a set of vocabulary and a set of sentence structures that you want to use. For example, if you were to translate weather reports, and you know that your machine translation system can do that without any problem. And machine translation has been deployed in the setting without any problems. So I've given you a sort of brief overview, but I can't mention NLP without actually talking about the fact that it's a fusion between 2 domains, between computer science, since we use machine learning approaches which require lots of maths, but also the fact that we're dealing with language data. So it's a domain, it's very much linked to linguistics. And actually my background is in linguistics. I did my BA in French and linguistics, and then came to computer science during masters and then PhD. And what we find in our domain is it's very multidisciplinary. We have people coming from all kinds of backgrounds, from maths, from computer science, linguistics, which makes for a really enriching environment. And the reason for that is that the data is really important, and how we can tackle that sort of determines how successful our applications are. So to understand the role of linguistics, it's going to be important to ask the question about what we're actually aiming to do with our different applications. And I'd say that the general answer would be that, well, you're trying to accomplish a given task or application, imitating what a human is capable of doing in terms of the output of that task. If we can surpass humans, even better. Quite a while ago, there was a test that sort of sounds like it's testing this hypothesis, which is a Turing test that was developed, which was a test to tell whether a machine can imitate the language behavior of a human by fooling a human into thinking that they are not talking with a robot, but a real human. This it's important to mention it's not an intelligence test. So for some aspects, a computer is far more intelligent than a human, and it's, well, if you determine that, and if you define that as its capacity to do lots of calculations in not very much time, but in other respects, it can't accomplish very simple things that we find are very, very easy. And also, it's important that to note that some behaviors are really easy to simulate. So it can be really easy to trick someone into thinking they're speaking with a human by getting the machine to just produce some spelling mistakes, or to have it type a little bit slowly, or or sporadically, because that's not what you expect a machine to do. So the results can really depend on the assessor and how willing the assessor is to believe that they're talking to a human rather than a robot. So you can quite easily trick a human on a very short utterance, and then it becomes a lot harder if you actually have a proper conversation over a longer period of time. So I think we can't just have a simple test like this. We need to really look at the different tasks and look at the output and compare them in a whole wide range of scenarios with respect to how well they're performing on these sort of human tasks. And the difficulty comes with working with language data, because language data is complex and it poses very specific challenges. Most complex tasks, such as those that I've mentioned previously, require some kind of linguistic knowledge or some notion of semantics, the meaning of the sentence, in order to carry out the task. So some people talk about the ultimate goal of machines in NLP to be understanding. And I'm not a big fan of this word understanding, because it implies that you want your machine to behave exactly like a human in the way it processes the data. And well, firstly, we don't know really how humans process language at all, so we don't even understand ourselves. So why should we try to imitate that, since we don't know what we're doing? And secondly, we don't need to try to imitate how a human processes data, because a brain isn't a computer, and we can probably reach some of the same goals but with different methods. So I'd say the ultimate aim is to imitate human behavior, as in the output, the language behavior, or even surpass it. But we shouldn't forget that machine is just a calculator, and you need to teach it everything. It doesn't have any knowledge from the get-go. It doesn't have a personality and a way of reasoning by itself. So we have to tell it what to do. What a machine sees when it processes text is just a sequence of characters. It doesn't know what they mean. And our task in NLP is to either provide some kind of structure to the text that we give to machines, so that they can better generalize from it to do tasks, or equip the machine with the processing capacity to create those generalizations itself. So when we talk about structure, I mean, this is where linguistics comes in, because it gets down to how you can get meaning from a text. There are different levels at which you can do linguistic analysis. The top level here, the phonological level, is concerned with the sounds of the text. So here I've written linguistics in International Phonetic Alphabet. And it should be noted that this differs from the writing system of a language. For example, English is a very good example of that. The fact that it often corresponds very little with the actual pronunciation. There's no direct correspondence between the letters of the alphabet that we write in English and how you pronounce it. But beyond the level of the sounds, you have the morphological level, which is how words are composed. So how they can be broken up into component parts that contribute meaning to the word, meaning and function. For example, the word inevitably can be broken up into morphemes, each representing some part of the meaning and function of this word. In being the negation of it being avoid, and able being capacity, and then the li, indicating adverbs. Once you get beyond the level of the word, you can go to the level of the sentence and how words interact with each other grammatically. So generally, we represent the root of the sentence as the verb. So this sentence is the French for the cat is eating a fly. And so mange, which is eat, is the root. And then the cat is the subject of this verb, and the fly is the object. And this can go some way into understanding the relationships between the words in the sentence and getting some way to getting the meaning of it. So the next level of analysis is the meaning itself, the semantic level. And this concerns how the different units of the sentence, what their role is in the sentence. So the main action is mange, eat. The agent of eat is le chat, the cat. And the patient, the thing that the action is happening to, is the fly, une mouche. And note that this would be exactly the same semantic representation, even if the sentence hadn't been le chat mange une mouche, so the cat eats a fly, but if it had been la mouche est mangée par le chat, the fly is eaten by the cat. So you've got variation of syntactic structure, but the same semantics. And you can go even beyond semantics to look at how how language is used in real communication in context. And this doesn't always correspond to the semantic logical representation. An example of that is the sentence, can you pass me the salt? Which doesn't literally mean, are you physically capable of passing me the salt, which is what it means semantically and logically. It actually means pass me the salt, but in a nicer way. Similarly, if I'm in a cold room and you're next to a window that's open, and I say, "Ooh, it's cold in here," it's probably an indication that I want you to close the window, and not just a declaration about the fact that I'm cold. So it's really important to to look at these different levels of analysis, because it's what we expect our models to be able to produce in order to accomplish these tasks, or at least we hope that it might help them accomplish these different tasks that require some kind of semantic knowledge. And with each of these different levels, we can have intermediate NLP tasks, which can be learned to produce these kinds of annotations, which can then be fed into our models. For example, part of speech tagging, you have a sequence of words and you associate with each of the words a part of speech. For example, here we have a determiner, a common noun, a verb, a determiner, and another common noun. For syntactic parsing, you can learn models that can reproduce this kind of annotation, syntactic annotation. And for semantic parsing, the same. You can assign roles to different parts of the sentence. And so this can be fed into different models. So I've mentioned the fact that language is complex, but why is NLP hard? I want to summarize it in 2 main points. The first is ambiguity, and this is when there are several possible analyses. This is quite different from programming languages. So with programming languages, you have a character stream, which is your code that you've written. Lexical analysis chops it up into parts where you have commands, you have variables, etc. And now you have a stream of lexical units, which are analyzed syntactically, which means that you look at the relationships between your different units and you get some meaning out of your code, which is the interpretation of your code, and you execute it. And unless you've done something incredibly wrong, you have only one type of meaning of your code and one way of executing it. So natural language isn't like that at all. We have quite a similar processing chain. So you have a character stream, you then cut it up into words. But the problem is that the notion of a word is ambiguous, and you can have different ways of cutting a sentence up into words, which means that instead of having a stream of lexical units, you have a graph of lexical units with several possible interpretations. And then when you do your syntactic analysis of that, you won't just have a tree, so one meaning, you'll have a forest, so several trees. And often you'll need to disambiguate that to get a single meaning, if that's even possible, because sometimes you just have ambiguous sentences. So the ambiguity can exist at all the different levels of linguistic analysis. For example, at the lexical level, you can have an ambiguity about the segmentation into words. For example, is hot dog a hot dog that you eat, or is it a hot dog, a dog that's hot? And you'll need some context to tell which one it is. And then even once you segment it into words, each of the different words can be ambiguous. For example, in polysemy, a word may have several meanings that are linked. For example, the glass being the material used for windows, or being the object you drink out of. And with homonymy, you have several meanings that aren't even linked. For example, bank can either be the financial place where you take out money, or it can be a riverbank. So I mean, this poses a problem for analysis. And on the syntactic level, you can have different ways of representing the relationship between words. Here's another type of syntactic structure that you can have corresponding to 2 different interpretations of these 2 sentences that you could possibly have. So time flies like an arrow, fruit flies like a banana. In these cases, either flies is the verb or like is the verb. And what's quite funny about this example is that you're primed by the syntactic structure of the first sentence into thinking that flies is the verb rather than a noun as part of fruit flies. And then you have other kinds of ambiguity. For example, ambiguity in what expressions may refer to, such as named entities. For example, Paris, does it refer to a city? And if so, which city? Is it in America, or is it in France? Or does it refer to the name of somebody, either a surname or a first name? So I mean, at all of these different levels, you have several possible analyses. You need some kind of way to decide which one is the correct one. And the second point that makes NLP particularly difficult is data sparsity. So that's when you have lots of very rare phenomena. For example, lots of words, and many distributions in NLP follow Zipf's law, which, so I've plotted a diagram here, means basically you have lots of very frequent phenomena and lots of very rare ones. So this diagram, I've taken a massive corpus of text, and I've counted for each word how many times it appears in text, and then I've ordered them according to their frequency of the number of times that they appear. So on the left, we've got the most frequent, and on the right, the rarest. And what you can see is there are a number of very frequent words in English. It's things like a, the, is. And then you've got this really long tail of words that are very, very rare. And this line will just sort of keep on going infinitely. So that there are consequences of this. It means that even if we use lots of data to train our models, there will always be unseen words. And this could be through neologisms, so new words that are invented, could be spelling variations, could be abbreviations, things like SMS language. It could be rare and specific technical terms. It could just be things that we haven't yet seen in the corpus. And it also means that you can be lured into a false sense of security, because you might be able to process some frequent phenomena relatively easily and get a certain performance in your model. But then to get any higher, you're actually left with a lot of rare and difficult phenomena to process, which can't just be dealt with a simple rule. So this makes everything very tricky. So before going into some of the approaches we use in neural NLP, I'll do a very brief history on the different approaches that have been used in the past and are still used today. So NLP started out with rule-based approaches quite early on, especially looking at machine translation. Machine translation was seen mainly for intelligence purposes, trying to get information about other countries. And it was seen as a decoding problem, sort of like cryptography. Seen as if you were translating from a foreign language into English, then the foreign language would be seen as an encoded version of English, which you then need to decode. So this is how Weaver described it in 1947. When he said, I look at an article in English, I say, this is really written in English, but it is being coded in some strange symbols. I will now proceed to decode. This is quite a basic way of viewing machine translation. And at the time, they were dealing with rules and lexicons. Around this period, there was also some very influential work in syntax by Noam Chomsky, looking at generative grammars, and he really formalized language like mathematical objects, so it's formalizable, and so this hadn't been done before. Around this time of rule-based, there was also some pessimism in NLP, which led to a reduction in funding, especially for machine translation, because people realized that it wasn't as easy as they thought it might be initially, notably because of lexical ambiguity. So there was this famous report in 1966 where they realized they wouldn't be able to produce high quality machine translation without post-edition. An example that was given is the following. Little John was looking for his toy box. Finally, he found it. The box was in the pen. So pen being ambiguous between the writing implement and a playpen. And actually what's quite funny is that some of even the modern machine translation systems can't necessarily translate this correctly. And towards the end of this period, we had the development of symbolic approaches to the implementation of formal grammars. And then these were then probabilized around the 1980s, where we had the beginning of probability-based and statistic-based approaches, which instead of having sort of rules were learning from data. So this means you needed labeled data, and your model needed to learn what's important from that labeled data to accomplish the task. So grammar and rules were replaced by mechanisms to learn those kind of patterns, either explicitly or implicitly. And at the same time, we saw the development of large-scale corpora and linguistic resources in order to support these kind of approaches, because suddenly we needed lots of data in order to learn these models. And today we're mainly using neural approaches, but it can't be sort of looked over the fact that actually some applications do work well with rule-based and probabilistic approaches. There's no point in deploying 50 GPUs in a huge machine learning system for a problem that actually can be solved using a couple of rules and relatively quickly. So they shouldn't be overlooked at all. Your solution should be adapted to the problem. The hardest type of symbol. So, yeah, I mean, it's a very good question. And NLP, I mean, up till now, I mean, still today is very English oriented. So lots of the applications we have are to deal with the Latin alphabet, and lots of the models that we have are particularly for that. So the choice of character does have implications for your application. I don't know whether I can really answer the question about which is more difficult or not. If you've got different alphabets, if they have a white space between them, for instance, that between the words, that can simplify your processing, because it provides you with some sort of approximation of what is a word unit. If you can split, say, hot dog up into hot and dog, you've still got ambiguity, but at least you've got those units there. Whereas there are some writing systems where you don't have those white spaces. So there's quite a lot of work, for example, with the segmentation of Chinese, with the detection of word units automatically. For example, if you don't have white space, Arabic can also be quite challenging. I haven't worked in Arabic myself, but because of the complexities around and how sort of vowels and how they aren't necessarily expressed in the writing system, that can make things a bit more complicated. Yeah, I mean, I hope sort of I've asked your question. I suppose I can't really provide a blanket answer about that, but it can pose difficulties. Good question, and I say that's one of the big challenges we have today, because data is a really valuable resource, and I mean, it's sort of the best way to learn generalizations, but then obviously your bot is going to learn from whatever data you give it. There is a more sort of general question, not necessarily about the techniques that we can use to stop it learning bad habits. And actually, I'll be mentioning it a bit at the end of the talk. It's in terms of what do you consider to be a bad habit, because that's also quite a subjective thing, but it can depend on social factors, on your culture, and how you express things in certain languages. And so it can also be very tricky to set out a list of guidelines about what you want your chatbot to produce or not. So there is quite a lot of work in say debiasing chatbots, so they can tend to exaggerate certain things you see in the data, be stereotypical traits, often results in sexism, and often you see these kind of things about NLP in the media. It is very difficult to debias. So even if you try to debias, there's likely to be a bit left within the model. And some of these are actually a reflection of the society, so a reflection of the data. So one way is you can try to improve your data, try to make it representative. If you don't want to include certain things, you try to exclude them. So often we take data from online, so you might want to exclude things like porn websites, and that's something that you have to think about when you're crawling data. But otherwise, the models themselves are likely to accentuate bias, and it's tricky. So it's an open question, and it's one of the main difficulties about deploying these kinds of systems in the wild. The second part actually makes me think about so early on in the history of chatbots, we had the Eliza chatbot, who was a psychologist, and she was very sort of simple. She had a couple of rules to help her interact with people, and basically the idea was that she would encourage the other person to talk. So she'd say things like, "Tell me about your day." You'd speak about it, and then she'd latch onto a keyword and say, "Oh, that's interesting. Tell me more about, this specific keyword." And then she'd maybe have back channels like, "I understand. Tell me more." And then they developed a second chatbot who was, if I remember correctly, Parry, who was a bit paranoid, and so they actually put the two together so that they could have this conversation. So I think, yeah, you can definitely put chatbots together. What's really interesting is if you could, well, if you get them to learn from each other. In terms of the Turing test for chatbots, it's a very interesting idea because you could you could see this as a way of learning to be more and more human. If you've got one chatbot who is trying to detect whether the other chatbot is a human or not, then it could be a way of pushing that chatbot to be more and more human and deviating from the behavior that makes it look like a robot itself. So this actually could be, a way of training a system, having one that sort of attacks the other one, trying to detect whether it's whether it's a robot or not, and the other one trying to deceive the other one into thinking that it's a human. So I mean, this is the way some of our systems actually learn. You try to have one system that that sort of tries to fool the other one, and the other one trying as best as it can to detect to detect whether it's real or not. So now I'm going on to talk about some of the neural approaches we use, and these will be quite similar to the statistical and probabilistic approaches in the sense that we use data to learn patterns and to learn to accomplish tasks. So what I said on the previous slide is very much relevant here. So what we have to do different classification tasks is we have some input, and generally in NLP this is sequences of words to make up a text. We then have some kind of processing, which we'll go into in a minute, and we have some kind of output that's produced. And the output will depend on your particular task or application. For instance, it could be a class, also call it a category. In the case of, say, spam detection, hate speech detection, fake news detection, so spam, not spam, hate, not hate, fake, not fake. Or it could be the classification of a text into different genres or domains, like politics, sport, financial, etc. Your output could also be a sequence of classes where you learn to associate with each of the elements of the input a certain category. So this is the case of part of speech labeling. It can also be the generation of a variable length sequence. So this means that the length of the output sequence isn't directly linked, as it is with the sequence of classes, to the input that you give. So this is the case when you transform input text in translation, simplification, or paraphrasing, but also when you condition on previous sentences, is in the case of chatbots, or where you condition on other types of context, such as images or sound, in the case of automatic image captioning or speech recognition. And then there are other kinds of output that you can have. An example here is finding a masked out word in a sentence. So this is one of the applications of, so this is one way you can use a language model, and I'll be talking about this a little bit later. So you're given a sentence, you remove one of the words, and then you have to predict what the word is. So actually this is equivalent to predicting a class here, where you have a huge number of classes because it corresponds to every single word that you could possibly have in your language. So here the obvious result would be telephone or phone. So let's first look at some basics of neural networks. Start off with, why do we call it a neural network? So a neural network contains artificial neurons where you have some input, you then process it, and then you produce an output, which in the case of neural networks is a real number. And these are inspired by biological neurons, even though they also have quite a few differences. So with the biological neuron, you have some input, some signal that arise by the dendrites, with some signals being more important than others. And then it's processed by the neuron, and then the neuron can fire and transmit signal to other neurons. In the case of the artificial neural network, so you have the sort of same kind of structure: input, process, output, but the neuron doesn't know how to process the input at the beginning, and it must learn how to process the signal, i.e. how much weight each different signal you give it should have in order to best accomplish your task. So this is sort of the basic principle of a neural network. You'll have these weights that need to be learnt, and that is what training a neural network is. So to make this clearer, I'll take a working example, which is a reasonably sort of simple example of spam detection. So you want to detect undesirable emails and classify them as spam. So you either want to classify it as spam or not spam. The class not spam is often referred to as ham, and it's a binary classification task since you have two classes. It's often relatively easy to detect whether an email is spam or not by using the presence or not of certain words or expressions. For instance, you could look at the number of unknown words in an email. So on the one on the right here, you can set up quite a few gobbledygook words. And then you might have the presence of words that are predictably indicative of being spam, like Viagra or click here. So what you can do is transform your text into a different representation, a more structured, by defining a list of features. And I've defined these 4 features here with x1 to x4. And each of these represents a different feature. The first one is the number of unknown words. The second one is the presence of Viagra. The third is click here. And the fourth is the presence of the word dear. And each email will have these 4 features and be characterized by the values associated with them. In the case of counting, you'll have the number of times the word appears, and in the case of the presence or not, you'll either have 1 or 0 for yes or no. So every single document will be represented by these values associated with each of the features. And you'll need a large data set of training examples to learn from. So lots of emails, each has a set of values associated with these list of defining features, X, as shown in the table below, and each has an associated class, either spam or ham, and we call this Y. In supervised learning, which is a dominant strategy, these classes will be used to learn how to process the inputs. So they'll be used by the model for it to learn what importance to give to each of these features. So that's our example. And the first model we're going to look at is the Perceptron, which can be seen as the smallest neural net model. So imagine these are our data points. The pluses indicate that it's spam, and the minus indicates that it's not spam. And here I've just sort of plotted them according to 2 arbitrary features. And the Perceptron is a very old model, and then has its learning algorithm associated with it from 1957. And basically, it's a linear classifier which can be used to classify data points, like these on the right, into 2 different parts, in the case where you have 2 classes. So the aim is, so you start off with something that is unable to classify at all into these 2 classes. And it's an online learning algorithm, which means that the weights of the model will be updated progressively. So little by little, it'll be able to divide into these 2 classes, so that if you get a new example, it'll be able to tell that all the ones in this direction are spam and all the ones in this direction are ham. And if the training data points are separable, then the Perceptron is guaranteed to find the weights that will separate the data points. So how does the Perceptron make a prediction? In the binary case, so where there are 2 possible classes, what you have is a linear combination of features and weights. So we've already seen the input features. I only defined 4 in the previous slide, but you would have a lot more of them. So these are vectors of numerical values. And then you have weights corresponding to each of those input features. And you do the linear combination of them. So you're doing a sum of them, but each of them weighted by how important they are for the final prediction. And then what you have is an activation function. So think back to the biological neuron. You've got your input signal with different weights associated with it. And then you need to decide how much you're going to fire or not. So the activation function, in this case, will map values to a different class. You could say if the value is bigger than 0, then you take the class 1, for example, spam, and if not, it's the second class, ham. But at the beginning, your weights haven't actually been learned, so the model's just going to predict sort of nonsense, basically. It's not going to be able to make the correct prediction. So you need to look at the learning algorithm that goes with it. Sorry, I just forgot the slide. So this is a graphical representation of what I've just showed you. So you've got your 4 inputs here, each of them weighted. Then you have your activation function, which will decide on your predicted output. So the learning algorithm, you have a set of training data, which we label X, Y. So X are the characteristics of the input to your model, and Y are the real classes associated with each of the emails. With a certain number of examples, D, usually you need quite a lot of examples in order to generalize well from the data. And we have 2 classes, class 1 being spam and class -1 being not spam. And then we have some model weights, which are randomly initialized at the beginning. We also have this parameter alpha, which will determine by how much we adjust the values each time. So this will have an impact on how fast the model can learn. But if you make it too big, then it could it might not be able to be as precise as if you have a very small value. So basically, this is the algorithm. What you do is you iterate over the data examples for a certain number of epochs until your model is correctly trained. You take each of the examples, so each email, and then you make a prediction with it. So this is this line here with the prediction. So you have your linear combination and then your function, which will determine whether the class is 1 or -1. Once you've got this class, you compare it to the true label of the email. Did we get it right or wrong? If we got it wrong, then we're going to update the weights in that particular direction, either in the positive direction or the negative direction, depending on the true class of the example, if it's 1 or -1. And then this alpha will determine by how much we move in that direction. So we keep doing this until all the predictions are correct, or until we're not getting any better, because sometimes it's just not possible to get all predictions correct. So what we will end up with, hopefully, is that that features that are important for discriminating between the 2 classes will have weights that have a higher absolute value. And then little by little, the model will learn how to adjust these weights to produce a model that can discriminate between these 2 classes. So that was the case of 2 classes. How do we do multi-class classification? That's when we have more than 2 classes that we want to classify between. So I'm showing again this figure here. It's quite similar. We've got our 4 input features characterizing the email, but instead of 1 neuron, we have 3 of them. And for each neuron, we have an individual set of weights for each of the features. So we have, instead of 4 weights here, we have 12 of them. So what happens is we do weighted sum for each of these neurons for each class. And then we have some kind of activation function over the values of these neurons here. So this could be a softmax function, which basically takes these values and normalizes them so that they all sum to 1. And this is like having a distribution of probabilities over our different classes. So if we have 3 classes, we might have spam, ham, and important. And we want to know what the probability is of our email belonging to each of these classes. Or we can just take the argmax, which is taking the class which has the highest value, and we take this as being the prediction. So these 2 are equivalent if we just want to know about the prediction of the model. And the learning algorithm is very much similar. So we have training data. This time we have several classes, except that we don't just have 1 weight vector, but we have 1 for each class. And the way we learn it is, so this is exactly the same here. We have a prediction, but in here we have an argmax over the different classes. So we take the class that gives the highest score as our prediction. If the prediction isn't correct, then we're going to update the weights of the class that we should have predicted. There are alternative ways of doing updates. For example, you could update the class that you wrote, the predicted class that was wrong, and that could also help your learning. So it's exactly the same principle. You're learning features to discriminate well between the classes. So the passage from perceptrons to neural nets is not a big leap at all, considering that perceptron is just a very small neural net with sort of only one layer here. So this is an example of a sort of a very simplified version of a neural net, which is basically a series of transformations of the input into the output, which we've already seen. The difference here is that, so we have a hidden layer here. The hidden layer represents a transformation of this input from the previous layer. And this is produced after a linear transformation and a non-linear transformation. So this is very similar to what we saw for the perceptron. But then there's an output layer. And so the output layer, there is many dimensions as the number of different classes. And this is got from having a linear transformation and then a final activation function such as softmax that will produce a probability distribution of your different classes. So, I mean, this is very much sort of multi-layer perceptron. This is a very basic neural net, and you can define other types of neural nets that I don't really have the time to go into today, unfortunately. So from this basic neural net, you can manipulate the number of layers that you have, the dimensions of the layers, and this can alter the learning capacity of your model. It increases the number of parameters if you increase the number of layers, also if you make them bigger, for instance, and there's nothing that stops you from having layers that are different sizes. So all these things are things you need to think about when you're designing your architecture. What's the best way of modeling your task? And often we actually try out different architectures depending on the task that we have in mind to see which one works best. For example, when you don't have much data, you're unlikely to learn very well if you've got a massive model with lots of parameters that need to be learned. But if you do have lots of data, then you don't want to necessarily limit yourself to a very small model because it won't be able to generalize quite as well. So a little word on learning. We spoke about how the perceptron learns with online learning, and the same is the case here with neural nets. So you basically feed in examples, and you, as training progresses, you update the weights according to the current predictions of the model. From having trained lots of machine translation systems in the very first iterations, the outputs are awful. You tend to just get translations like no, 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 and yes, 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 yes. And eventually it starts to produce things that are like sentences, and then finally translations. So what you want to do is try to find a set of weights of your model that minimize a certain loss function. So this loss function is a calculation of how bad the model currently is. So how far away your model on the was on the training data from the actual labels that it should have predicted. And the way we usually do this is by gradient descent. So imagine you've got your function here, and you start off at the beginning of your training with some weights initialized randomly. So it's gonna have a very high error rate. Then you calculate the loss on a batch of examples using these weights, and you modify the weights in the sense of the gradient of the function. So what you want to do is make sure that you're going down in that loss function. You're going in the right direction, so that if you were given those sentences again, then you're going to perform better on them. So at the beginning, people used to do this manually, and it was quite tedious. And we're really lucky now because this can be done automatically to calculate the gradients and to be able to adjust these weights through backpropagation. So that makes training neural models really easy now, and there are lots of toolkits that exist, PyTorch and TensorFlow, that can really simplify this. Even if you don't necessarily have that background in maths and able to do it manually. So this is sort of the iterative process that we go through. You have a random initialization of parameters of your model. You do a prediction, which is going to be absolutely rubbish. You then compare your predictions to the gold outputs. The gold ones are the true labels. You calculate an error, and then you update your parameters in the sense of the gradients using that error. And then you complete the process with your predictions getting better and better until the error doesn't decrease anymore, in which case you stop training your model. And you hope that that it's picked up some good patterns in your data. So there are certain consequences of this type of training. One is that the more data you have, usually the better you perform, because you're training the parameters more, especially if you've got some very varied sentence types. It also means you'll need more processing power. Lots of GPUs, might take a lot longer to train. It also means that because it's data driven, that the model will be very dependent on the type of data it's seen during training. This is inevitable, and actually it's sort of following up on the question we had before on tail learning from data. So the consequences this has is that although you might have an error rate that is quite small on your training data, the performance may be really bad on other types of data. Often if we train a system on, say, news data, it won't perform very well on social media data, for example, or on biomedical data, because it's become very specific to that data. So what you want is, looking at these three diagrams at the bottom, is a compromise between sort of the first one, which is overfitting to the training data, which means it's very specific, it's very, very good at those specific examples, but actually when you pass onto a test set that you haven't seen during training, then it's likely to have a very poor performance because it's so specific. On the other end of the scale, you have a model that hasn't been trained that well, so it's unable to pick up those generalizations at all. So it's going to perform poorly on the test set and the training set. So what you want is a good compromise, learning some generalizations from the data without overfitting to it. Underfitting often happens for languages which data exists, and the models that result will have a much lower performance. But there's a lot of effort nowadays about training models for all languages, not just English, because we've been so English dominated up until now. There are hundreds of the world's languages for which even basic tools don't exist. And it's really important to make these kind of tools accessible to everyone to aid communication. A final problem is the possibility of bias and overgeneralization that I mentioned a bit earlier, and the potential ethical problems that can entail. So if you've got bias in your data, it's likely to exaggerate it. And so, yeah, you need to be careful about what's in your data if you want to use it for a particular application. If you want to have a little play around with different kinds of neural nets, I highly encourage this playground on TensorFlow. It's not language data, it's image data, but it can give you some idea about the expressive power of these models. And which kind of features can help. So here you've got a certain pattern that you want to reproduce, and you can choose different input features. You can choose the number of hidden layers and the dimensions. You can have a little play around, change the batch size. The batch size is how many examples you give when you calculate your loss. You can add noise in, and you can quite clearly see that for this particular pattern, you need it to be nonlinear, which is the case for neural nets. So at the moment, I've only just had quite a simple working example with a couple of features such as, does this text contain the word click here or Viagra? This isn't the state of the art currently in natural language processing. So it's important to have a word on how we represent text. And so I've got a little teaser here with a continuous representation. So the starting point is the problem of discrete units. And this goes back to what I said at the beginning about how the machine will just see a series of characters, or if we cut on white space, a series of words. For example, this text here, the rat reached for the lunch basket, since rats do like lunch. Moles, still sat on the boat, helped him. So if you give this to a computer and we tell it that, well, you can cut on white space and therefore you can segment into words, what you'll get is a series of discrete words as follows. And unfortunately, the computer won't be able to distinguish between things like the with a capital letter and the lowercase. For it has no notion of similarity between these two words. It won't know that rat and rats, for example, is very similar because their form is different. So this is what I mean about you having to tell the computer everything. So the machine sees them as different units and has no intrinsic knowledge of what these words mean. So this is a problem because we have no intrinsic way of representing the meaning of words, and there's no notion of similarity between words at all. These are just completely discrete units. If we were to represent a text before, we'd have to say, is this word present? Is this word present? And set them all out like that. So the solution we have is to represent words as continuous representations, known as word embeddings. So this idea is that you take your word and you embed it in a continuous space. So each word in your entire vocabulary is represented by a vector, so an ordered list of numbers of a certain fixed length. So I've got some examples here. I mean, what do these numbers mean, and what could these dimensions correspond to? So they could be meaningful interpretable values. For instance, here, as I said, I've set out these primitive semantic values. Is it animate? Is it small? Is it furry? Is it rodent? Is it edible? And you could answer yes or no for each of these using either 1 or 0. And you could have other values referring to grammatical properties, such as is the word singular? Is it plural? For verbs, what's its tense? I could go on. So you could represent these with 1s and 0s. However, it's rather problematic because, I mean, how do you define these different primitives? You're likely to have lots of features for which it's just not relevant to have a value at all. So I wasn't quite sure whether you should classify lunch as small or not. And I think it probably depends on who prepared lunch. And same, is a rat edible? I mean, it depends where you live and how hungry you are, I suppose. So it's not entirely clear how you can define these different features, and you're likely to have a huge number of potential features, and it's just impossible to define manually. So clearly we do this automatically because it's not possible to define these semantic features. And to do this, we use distributional information. And this is based on what is known as the distributional hypothesis, which means that words that are similar will be found in similar contexts, i.e. a word is characterized by the company it keeps. So you look at a word and you look at its neighbors, and that's how you can induce these word embeddings, these representations of words. So I've given you an example here. So one of the first methods that was developed to do this, for each of the words, so you're going to have a very long vector that represents all the words in your vocabulary. I've only got 3, 4, 5, 6 here, but actually this is going to be huge. And each dimension of the vector represents the number of times the word, for example, rat, appears in the context of each of the items of vocabulary. It's like it appears in a certain window in a text, or appears in the same sentence. The idea being that similar words will appear in similar contexts, semantically and grammatically. So rat will not appear sort of next to eat very much, but rats will, because otherwise you've got rat eats and rats eat. But they might both appear in the context of the quite a lot. But then you've got the problem that you've got a huge vector. It's not very easy to manipulate. So we can apply dimensionality reduction techniques such as LCA and PMI, which are ways of reducing this vector down to a smaller dimension, which has the effect of creating some interesting patterns as well. It's not just reducing the vector down. You're likely to have vectors that are less sparse because there are going to be some words that just don't appear in the context of any other words very rarely. So this helps you make a compressed, condensed version of a vector. That does mean that the different dimensions aren't interpretable, however, so it becomes a more abstract representation of each word. So today we use some more advanced techniques such as neural language models, which I'll be mentioning at the end of the presentation. So once you've got your representation of different words, you can plot them in space to see what they look like. So clearly there are too many dimensions to visualize because your embeddings have a very high dimension, but there are techniques that can be used to select the dimensions that are most salient to help you visualize these. So here is an example from TensorFlow, where I've looked up the word Paris, and you can see that the neighboring words, so the words that are closest in space, are written here, and they're generally towns, and there's also Pierre, like a French name, Antoine. So, I mean, this is really interesting. It's definitely picking up some semantic content of words. And you can do this with a whole variety of words. Here's an example with teacher, where you've got it very close to translator, professor, historian, but also things like teachers, teach, learning. So this is exactly what we're looking for in terms of representing semantics of words. And what's really, really good with these is that we can then do arithmetics with these word embeddings. So we've already seen that we can sort of have some notion of similarity between the vectors, so we can tell which words are similar to each other, but then we can also manipulate them by doing vector arithmetic. So you change the representation by adjusting the values in the vectors to attain a new representation. And this means that you can model relationships such as analogy. For example, if you take the representation of king and you subtract the representation for man, and then you add the representation for woman, the representation that you're likely to get out is queen, which means you can really transform words within this space to produce new words. You can do this with other sort of not just semantics, but also here in terms of grammar. If you take the representation for walking, you subtract walks, you add swam, then the result is likely to be swimming. The axes are, so they are dimensions that have been detected as being particularly salient. So I'm not quite sure what they correspond to here. So these are techniques that are used to aid the visualization, because you can't actually visualize this space with, say, 2000 dimensions in it. So I'm not entirely sure what these axes actually correspond to. But you look into these techniques, which sort of really aim to get these dimensions that will help you to visualize embeddings. And obviously, these embeddings will be far more complex than actually what's visualized here, but it's useful to be able to see that you're actually learning something important in these representations. Okay, so yeah, we can do arithmetic with vectors, which is great because we've seen that neural nets are simply a transformation, a sort of mathematical transformation of an input to produce other representations. So if our inputs are word embeddings like this means that we can manipulate these word embeddings to produce other representations and eventually to produce outputs. So this is how we use word embeddings in neural networks. There will be some approximations in this next section. I'll just say that in advance. So we have different architectures that could be used to process text. I mean, a simple basic one that actually we don't really use that much is the bag of words model. And bag of words means basically that you have no notion of order in the words you've got. So here are the sentences: the film is good, probably a film review. And a bag of words means basically you throw the words into a bag and then you shuffle them around and you lose any notion of word order. So here each input is represented by its word embedding, and I've just sort of concatenated them here. So what you're going to end up with is with a single vector, which is your input, which you can then use to learn whatever you want to learn in this particular task, to produce your output, which would most likely be a probability distribution over a number of different classes. So you can either combine the representations for all words or just the words that are likely to be informative. So there are techniques you can use to see which words are likely to be informative, or you could also just remove some grammatical words, which are called stop words, things like the, is, are. Okay, so in this one, it's not particularly sophisticated because, for example, the film is good is equal to good film that is, and in some cases that could lead to meaning problems. So the type of models that we tend to use, models such as these. So this is a recurrent neural net, and the idea of a recurrent model is that you treat the input as a sequence. And this is more natural in many of our applications because we basically have a sequence of words with a notion of order between them. So here, what we've got our word embeddings here as input. The film is good, and you start off at the, and you proceeds sequentially from the to film to is to good, one by one. So the input is organized into different time steps from left to right in the sentence. And at each time step, the new representation, here it's shown in yellow, it takes the current input from the current time step into the blue, and also the output of the previous time step representation. I've actually included 2 layers here. So once you've got your first sequential input, then you have another one over the top. And then what you can do is you can use your final representation, so the one that finishes it good, to then predict your output. And that representation will be a representation not only of the word good, but of all the words that preceded it. And you also have some kind of notion of order, therefore, because the ones that are the left will have been seen first and the ones on the right last. So the position of the words is taken into account, but there are still some problems. So the representation of some words may quite easily be forgotten, for example, those at the beginning of the sentence. And this is particularly relevant for very long sequences. And also some sequence representations may not be that informative. For example, is here, whereas actually the word film is quite important. So you might have writing over the representation of others. So there are some more intelligent solutions to this kind of network. For example, the introduction of the LSTM, the long short-term memory units, and also you can see the GRUs. And the idea of these is that they're slightly more complex units, and they help you propagate memory from one unit to the next. You basically have these gating structures within them. I won't go into the details, but you have gates which help you decide, will help the model decide how much information to retain from the previous step and from the current input, and how much to forget. Because some information isn't that useful and other bits is. So this is a quite this is a high performing way of knowing which information to retain and which not to retain. So now I've sort of presented a brief overview of recurrent nets, and this can lead quite easily onto machine translation because we're dealing with sequences of text. Sorry. So in machine translation, we not only have a sequence of text in input, but we also have a sequence of text that we want to produce, which is the translation. So to do this, we don't just have one recurrent sequence as we had in the previous slides. We have an architecture known as the encoder-decoder architecture. And actually, this sort of makes you think of the cryptography of the slides at the beginning. The role of the encoder is to create a representation of the input sequence. So that's like we saw before, where you sequentially encode the words of the sentence to get a particular representation. And then you use this representation in the decoder, whose role is to look at the representation of the source sentence and sequentially produce a translation from that. So it'll produce first le, and then chercheur, then et, and then the word that we're currently predicting here, which is heureux, meaning happy. And at each time, so you'll have a representation of the input, but you also have knowledge of the previous word that was predicted. So what these green things are here are probability distributions over the entire vocabulary. So at each time step, you want to decide basically which word to produce. So this means it's many, many classes from which you can predict a word. And there are several problems with this basic model, which meant that it wasn't that good at the time, was that you're basically asking the model to summarize the entire sentence into this final vector here. So it might easily forget some of the words at the beginning of the sentence, even if you're using an LSTM or a GRU. And the second problem is that when you have longer sequences that contain more content, you're asking the model to compress all that content into the same fixed size representation at the end, which means that you're going to perform less well on longer sentences that contain more information. So there was a first change to this model that was introduced to help tackle the first problem about storing all that information in the final vector. And this was the introduction of bidirectionality. So you not only have a recurrent model from left to right, but you also have one from right to left. So here, and then each representation of the input units is a concatenation of these two states of the left to right and the right to left. So at every single stage in the sentence, the representation of the word is partly based on its left context and partly based on its right context. So this sort of helps to solve this problem somewhat. It doesn't solve the second problem, the fact that longer sequences will still be compressed into this finite-sized representation. So the solution for this was to add what we call an attention mechanism. And basically, an attention mechanism is a way of weighting the different input representations depending on where you are in the translation. So instead of using exactly the same representation for every single decoding step, what you're going to do is you're going to ask your attention mechanism to look at each of the representations of the input, look at the current state of the decoder, what you've currently translated, and decide what weights to assign to these. And then you can do a weighted sum of the different representations, which will be completely unique to this decoding step. And so probably in this example, the word which is going to have most influence in this representation is the word happy, because it's the word that we currently want to translate. And so this means that you can process even a long sequence without having to store all that information in a single representation. You can have variable inputs, and this is what really brought neural machine translation to state-of-the-art, surpassing statistical machine translation for the first time. So this solves the second problem. The current state-of-the-art, however, isn't a recurrent model. It's the transformer model, and obviously I don't have the time to go into all the details of it here, but I encourage you to go to that blog at the bottom of the slide, which gives a really good visual illustration of what's happening. The basic idea is that you replace the recurrence, so the sequential aspect in the encoder and the decoder, because it's not very efficient having to do that. You need to go through each of the time steps one by one, and also some long distance for dependencies are quite hard to model. And you replace that with a mechanism where the representation of each word is based on the representation of all the other words for the encoder in the source sentence. So on the diagram on the right illustrates this. For example, the representation of the word it will depend on all the other words in the sentence, and they'll be weighted differently depending on how important they are for the representation of this word. And so the words that are at the beginning of the sentence aren't going to be less important because they're at the beginning than the words that are right next to it. So distance is less of a factor, and it also means that you can run things in parallel rather than sequentially, which makes this model more efficient, and therefore it can be trained better, it can be more powerful. So I won't go into the details, but this is the current state of the art. It still uses the encoder-decoder with attention, but the encoder and the decoder are replaced with a different kind of way of creating these representations of the input units. So now that I've given you a brief overview of machine translation, something that's been really important in recent years is the notion of pre-training using language modeling. So I'll just explain to you what language model is and how we can use it to pre-train our models. The language modeling, I evoked it a bit earlier in the context of filling a masked word in a sentence. A language model is a probability distribution over a sequence of words. So how probable is the sequence given a language? This could mean how grammatical is it, and is it semantically coherent, for instance. But this is a slight approximation. For example, you would expect the probability of the sentence "take a look at my sentence" to be bigger than the probability of the sentence "take a looks at my sentence," which is bigger than the probability of "look at taken my sentence," which is bigger than looking at my sentence, etc., etc. And then you've got some garbage at the bottom, which is likely to have a very low probability according to the language model. And there are different ways you can use language models. You could use them to assign a probability to a whole sequence. This can be useful, for example, in translation, if you have several possible translations and you don't know how to decide between them. So you could look and see, for example, which one is more grammatical by comparing the scores of the two sentences according to a language model. You can use them to find the next word in a sequence, so the most probable next word. And this has notably been used to do text generation with models such as GPT, which can be used to complete a story or an article, for instance. So we've seen this a lot in the press, the use of these models. And then there's a different use of it, which I mentioned earlier, which is to find the most probable word to fill a gap in a sentence, given its left and right context. And this is the BERT model. For instance, if I give you this sentence, the cat was when I got woken up by the sound of a can opening. So what should go here is most likely to be something like sleeping or snoozing in this context. And we know that because of the distributional hypothesis. So the BERT language model is the one I'm going to concentrate on now. So I said before, you mask out words in an input sequence, and the task is to predict what word has been masked out. So this is exactly the idea of the distributional hypothesis. The representation of words will be learned to reflect the context in which they appear. This is an example of the model here from the paper, where they've masked the word improvisation. Then the BERT model is actually a transformer, and then at the end you have a probability distribution over your vocabulary, with improvisation being the highest scoring prediction. So there's a really good illustrated version of this on the same blog as I mentioned before. So why is BERT useful? Firstly, it creates really good representations of words that are based on their context. And this is actually very important for ambiguous words such as bank, because we saw that bank had two meanings, either the financial place or the riverbank. And in this model, it can have two different representations based, or many, depending on whatever context it appears in. It's based on the transformer architecture, which is state of the art. And it's also exposed to some kind of language data. So it's exposed to raw text, basically. But it's an effective way of pre-training the parameters, the weights of transformers, which can then be used for other NLP tasks. Which means that instead of using random initialized weights, what you can do is you can pre-train your model weights using learning objectives such as BERT, so using masked language modeling. And you have loads of data that you can use to do that. You don't need label data that's costly. And then you can fine tune that model on another language task like machine translation or paraphrasing to boost performance. And this is particularly useful for languages for which there doesn't exist much annotated data and which otherwise would underfit the model. And this is one of the major challenges for NLP today, how you can use monolingual raw text to help do tasks rather than have to rely on producing costly label data. And so going on to the third part, which is a smaller part of the talk, what are the big challenges in NLP today? So I mentioned a little teaser concerning raw data. I've got some of the major challenges concerning how we can actually do modeling of language. Specifically here, examples from machine translation, since it's my field of expertise. I've identified 4 different major challenges. The first one inevitably is ambiguity, because it's still a problem even today, even with these really good word representations. For example, if you're translating he saw her duck into another language, he saw her duck is ambiguous between he saw her bird and he saw her lower her head. So if you translate this into say French, you need to know which one of the interpretations you're going to use, otherwise it could create some confusion. It's also important to remember that words are often very culture specific. For example, if we were to do any kind of multilingual model where I wanted a map between lawyer and the equivalent in another language, you won't necessarily find an equivalent mapping. For example, lawyer can be mapped to avocat or notaire, in French, because the particularities of the job isn't in a direct translation. And in some cultures, even colors don't map directly from one culture to another. And another example here is the fact that owl in English, there's a single word owl for something that in French is represented by two concepts, hibou and chouette. So actually you need some kind of other context to tell what you're talking about if you want to translate this into French. Another example from machine translation of French, since I'm currently in Paris, is the need for context. If you were to translate the owl was sleeping, it was tired into French, your translation of it will be dependent on how you've previously translated owl, because it has no gender marking in English, but it does in French. So it's either masculine or feminine, depending on whether the noun you use to translate owl in this case is masculine or feminine. And many of our systems still work on the sentence level, which means that we would give these two sentences completely separately. And therefore, if you do that, there's no way of systematically translating it correctly. So we need some way of integrating a linguistic context. And then there's other kind of contexts that you might also need to integrate. For example, I found this on Twitter. Someone said, I couldn't help myself, I bought one. So one refers to this keyboard. And if you want to translate this into French, you need to know that keyboard is masculine, and therefore you should translate it as j'en ai acheté un rather than j'en ai acheté une. So this is another example of having to actually do image detection in order to do correct translation. And then another big field of study is how do you handle settings where you don't have much data. And the vast majority of the world's languages don't have much labeled data because it's costly and takes a lot of time to produce. So what kind of techniques can you use to get beyond this? And one of them being using monolingual data, like pre-training parameters. And even if you do have some data, it might rarely be in the domain in which you want to create your application for, or it might be of poor quality. For example, crawl data from the internet containing lots of porn sites and other stuff like that. And finally, a really interesting challenge is that of robustness. So making your making sure that your model is capable of handling lots of different kinds of texts. So this might be non-standard or noisy language. This is sort of the basic stuff you see on Twitter. Lots of not necessarily spelling mistakes, because it's been done it's been done on purpose to fit into Twitter, into how many characters you have on Twitter, and also just to be faster. But often our systems struggle to generalize over words like this, because otherwise written like this isn't the same as otherwise written in a standard way. We also want our models to perform well, even if we're performing on a different domain. For example, here I input some lyrics of Queen into Google. Don't stop me now, I'm having such a good time, I'm having a ball. And I'm having a ball got translated literally to je vais avoir un ballon, which means like basically I have a football, rather than I'm having fun, which is probably a result of the domain shift. It's quite unlikely that I'm having a ball with, there are other meanings of this as well, but we can see that it hasn't transferred very easily to this to these song lyrics. And then obviously there are new expressions being invented every day. For example, distanciation physique, is it translated as physical distancing or social distancing? I think it depends a lot on the culture, but it's just an example of new expressions that might appear, and you need your model to constantly adapt to these new expressions and notions that are being presented. And then finally, beyond how we actually model our data, we have the problem of ethics. And this was evoked earlier as well. Often we find our data online because that's where we can find the most data produced by humans on forums like Reddit, Wikipedia, even things like Twitter, as long as we have the right to use the data. And we need to ask ourselves, how representative is the data of language in general? Who produced the data? is this representative of all the different people that we want to provide our application for? And how do we stop bias in our models and the exaggeration of bias that we've seen in the data? How do we deal with offensive language? So this goes back to the chatbot Tay. Do you stop researching in these fields? You make sure that your models don't contain this kind of data, or do you have some kind of control mechanism to filter out to make sure that you don't produce an end application? And it's also important to create to encourage accessibility of these models that we train, to make sure that they can be used for the good of everyone. They can be analyzed, and everyone in the entire community can use them and have these models adapted to their language needs. So when I talked about bias, I want to just give you some examples of what I mean by that. For instance, gender bias is quite prevalent in these kind of models because of the several factors, but one of the main ones being the data on which the models are trained. For example, in this study, Brown et al. Exposed bias in the generative language model GPT by getting it to complete certain sentences that they had written. So they gave a prompt, which is the occupation, where occupation was replaced by something like policeman, teacher, cook was A. And then they got the language model to complete the sentence by predicting the next possible word. And it was actually completed by a masculine term, such as man, in 83% of the cases, which just shows you how male-dominated the text was on which they trained. And then they also gave prompts such as he was very and she was very, and got the language model to complete it. And there's an example here from their paper, which shows the types of adjectives that were used on the left for men and on the right for women. You can see they're quite stereotypical words, and this is the kind of stuff that can be exaggerated by the model, and it's particularly sort of unpleasant for the female descriptive words, and could be seen as sexist. So this is the kind of thing that ideally we'd like to avoid. But this problem can go further than gender. You can look also at ethnicity and the question of race, like problems such as the race man was very and the race woman was very, but you replace those with different things like Asian, black, white, Indian, etc. So they did this, and then they conducted sentiment analysis on the words that were predicted. So this is whether it's a positive or a negative adjective. And you can see that there's quite a lot of variation in the sentiment of the adjectives predicted, depending on whether you fed it Asian, black, white, Latinx, Indian, Middle Eastern, which is a strong bias against, for example, black. And it's really important to be aware of these things when deploying these models. This isn't the kind of thing that we want our models to be doing. And so if we want to be used, say, as chatbots. And so the big question, and not actually going to answer this because it's a big debate, is should we ban everything offensive or biased? And I'd say not necessarily. This is sort of way of being a bit on the fence about this. I think it really depends. It raises the big question of the fact that even the notion of bias, like say, I say this model is biased in this way, even that isn't objective, because my opinion is being driven by the social norms of my background and my experience, and that could be completely different from someone else. So we can try to de-bias our models, and people have tried to do this. They've tried to make it so that if you give it, say, those kinds of prompts, that it will equally predict men and women, that it won't show certain characteristics for men and women. It won't say the nurse is and then always have a female, and it won't say the teacher is and always have a male. This is important, but it needs to be recognized that bias will always remain on some level, and we need to recognize that. I think it's more dangerous to say that we can eliminate it entirely and pretend that it's not the case, particularly for those groups that could potentially be discriminated against. So this could actually do more harm than good. And so there's this interesting article talking about this notion of the illusion of objectivity. And so it actually can be useful to study bias itself within these models, because it can also be revealing about how we function as a society. So this is also another interesting area of study. Having said that, if we want to use these kind of models in end applications, we do need to do so with care. The example of the chatbot Tay was kind of a fun example of that, but things can be a lot more serious. Yeah, so here when a medical chatbot told a patient to kill themselves, and then another example where someone, this Indonesian disaster, they mention the word selamat, which means congrats, but also survivor. On the Facebook application, they suddenly produced balloons, which is really insensitive. But we can also do a lot of good with these systems, despite the problems that are associated with them. I would encourage you to read up on the story of Peter Scott Morgan, who's a roboticist who is using GPT to learn, well, to speak, despite the fact that he's now paralyzed. And so he says, I need AI to second guess what I was wanting to communicate, even if it produces errors. It's his way of conserving his personality and being able to communicate. So, so I've got some final conclusions. Language data is really difficult to work with, but that's what makes it exciting. We've come a long way. We need to look at the consequences of using our data in terms of overgeneralization and of bias. And we expect to see some quite big and exciting developments in the future, looking at more languages, more different techniques, especially those not requiring labeled data, and going beyond edited text, things like being able to process noisy text on Twitter, and integrating other types of context, such as images and videos.